So here we are going to start with the dSPACE demonstration. How we are going to start the dSPACE. First we need to open the control desk and check if the dSPACE card is active. Here we can see the card is detected and it is registered. It will be red at the initial when we switch on the computer for the first time. So it doesn't matter. It should show the name of the card. This is the DS1103 PPC controller board. This should be detected and it should be shown. After checking this, we can open MATLAB. Choose RTA1103. This hardware is 1103, so we need to choose that. Now we need to type RTI to get the Simulink library of the dSPACE. Here open master PPC. Here you will get all the interfacing blocks, that is ADC, DAC, which will be of the main use for our experiments, current experiment. We can minimize this. Then we need to build the circuit. For that I have already built the circuit. We can open that for now. Now from this it is a sine wave block is given to a gain of 0.1 and is given to the DAC channel 1. This gain 0.1 is used because DAC will amplify the signal by 10. So we are dividing by 10 such that our original signal is regained again. And from channel 17 of ADC we are giving to a gain of 10 and giving to the scope. This gain is because the ADC will scale down the signal by 1 by 10. So we are multiplying by 10 to regain the original signal which is acquired. Using this setup, we will be conducting various experiments. Before that, we need to open the model configuration parameters. And then go to code generation. And then go to browse and choose RTI 1103. Here we can see there is RTI 1103 that is already selected. Then we need to go to solver. We need to uncheck this. I already did, so it is unchecked. And here also we need to uncheck the input and the initial state. That is from the data import or export. And then we can click apply and then OK. After doing all this, we need to save this file. After saving this file, we will only have this in the new folder we have created. Copy the path of the folder and paste it in the MATLAB path and press enter. After doing this, we need to click here, build model. it will build the model and it will create a control disk SDF file. From this you can see it is completed. It has built the model and a new SDF file is generated. Now we need to go to directly. This is the file which is generated. We need to open that. First we will do the first part. Only this part we will continue. That is, we will generate a sine wave from the PC and realize in the hardware scope. Go to File, New, Project Experiment. Copy the path here. You can have a new name. Next, this should be selected. That is, this is the hardware board. It should be selected, and then we need to import the file. This is the STF file we generated. We need to import that. Now we will do the first part. We use a plotter. And then now go to View, Control Switch Bars, Variables. First we are only going to see the first part, that is sine wave to the real world, to the scope. So we will take the sine wave, output of the sine wave to the scope, and the frequency of the sine wave to the now. After this, we will start measuring. DC channel 1 we need to connect, and we are giving to the channel 1 of the CR. From this we can see we are able to realize the sine wave which is generated here. Now I am changing the frequency, making the frequency more higher, and we can see the change in that, and the change in frequency can be seen. And we can go stop measuring, go offline. Now we will go for the second part of the experiment, that is the real world signal generated from the signal generator is given to the ADC block, that is it is given to the ADC block of channel 17. That should be realized in the dSPACE. That is like this part, ADC from channel 17 is given to the system PC. We are going to realize it with the same. Since we already built this, we are continuing with the same file. Create a plotter to see the ADC value, and go to View, Switch Control Bar, Variables. We need to see the scope value, that is input to the scope. That is from the diagram. This value we need to see, that is input of the scope block. So we are choosing scope, and input of the scope we are chosen. Now go to Home, Start Measuring, we can click. Since now there is no result, we didn't switch on the signal generator. First we are taking 1 hertz. Amplitude we are fixing it 4. That is our wish, we can fix anyway. Let us say I am fixing to peak as 2. Now we can switch on the output. And from this we can see there is we are able to realize the real world signal in the dSPACE control disk. Here I am changing the frequency again. Let us say I am putting 10 hertz. Now there we can see it has reflected in the control disk. Now this completes the second part. Now we will go for the third part. That is, we are going to check if DAC and ADC are working fine. Like, we will give this sine wave to DAC and connect DAC to ADC directly and check the output that is, check the input to the scope. That is the if the ADC able to collect the value from the DAC and give the same wave. So for that we are going to do is use the plotter. We can use a knob because we are giving the input from the system itself. Go to view variables, sine wave output, that is the input we are giving to the DAC, and then scope input, that is the output we are getting from the ADC. From the ADC the value we are getting as the output, and to control the frequency I are giving it to the knob. Now we can go home, start measuring. From this we can see both the values are same. It is overlapping together. So it is both are working very fine. There is no difference in there. Now what we are going to do is we are going to check the lag compensator. That is, this DAC sine wave is given to a lag compensator which is in hardware. This hardware is a lag compensator design, that is series R parallel RC. Lag compensator we have designed for 100 kilo ohm resistance. R1 and R2 both are 100 kilo ohm resistance and capacitor of 1 microfarad. And now we are going to check the gain and the phase difference of the system due to lag compensator with the same, that is scope, that is the output of our system, that is input to the lag compensator, that is sine wave out, and the frequency control also we are having. The DAC from channel 1 is connected to the input, and the ADC is taken as the output, that is a parallel. Now we will go to home and start measuring. From this we can see this green color is the input we are giving, red is the output. There is a reduction in the gain, that is the reduction in the amplification and reduction in the magnitude, and there is a phase lag. We can see the phase lag from this. As you can see, there is a good amount of phase lag. We can easily notice that in this diagram. So we can ensure that our lag compensator is working fine. We go for the closed loop diagram. In dSPACE, general practice is the real system, that is the hardware is present in the real world. The system to be controlled is present in the real world, or the plan to be controlled is present in the real world, and the controller we will design in the MATLAB, Simulink or in control desk and check the system. But currently in the first phase we are doing the inverse of it. The control this is the lag compensator which we designed is in the hardware, and in the system, the plan to be controlled is in the PC. Similar to that, we have designed the Simulink diagram. Here the controller comes in, that is the lag compensator, and the system is here. This too is because for the lag compensator circuit diagram, there will be a 1/2 additional component which is coming in play. We don't want it, so we are multiplying by 2 and cancelling the unrequired gain due to this circuit. Now when it is directly connected without anything and without this without any controller, we will get a steady state error of 0.5, which will be seen in. From this we can see just the system in closed loop it is checked with a step response. From the simulation we can see that the system is settling at 0.5, so the steady state error is 0.5. We need to reduce the steady state error, so we design the lag compensator to reduce the steady state error, and we are using that lag compensator here. Now like the same initial step, we go to code generation, choose RTI1103, go to solver, remove this and go to data import export, remove these two, click apply and then OK. Then like before, we need to go to that folder, copy this, paste in the MATLAB path, and then build the model. Since the model is already built initially itself, it will be somewhat faster. No, it is starting from first. Now the model is built. Now we open the STF file created. This is STF file. We open it. Go to file, new, experiment, copy the path, paste the path in this, and do next. We can give a new project name since it is already there. Next, this should be there, just to ensure that, and then import the file. This is the STF file, close loop, open, and then give finish. Now that is done. What we are going to see as output is the error, that is the value from the sum block. The output of the sum block is the error, and input to the scope is the output of the system, closed loop system. We are going to see those two results. Open control disk. We can use two plotters, first plotter and second plotter. Then go to view, switch control bars, variables, that is output of the sum that we need to know, take, that is the error, and the input to the scope is the output of the system. Now we can go home, start measuring. From this we can see the system is, the steady state error is reduced from 0.5 to 0.37. So this gives this shows that our design is, the designed lag compensator is trying to improve the steady state error. And this completes the experimental part of the MTech. So this is the next part of BTech cycle, where sine wave input is given to DAC, and from DAC it is given to a RC filter, that is the input is across this one and output is across the capacitor, and this output is taken through to ADC and it is given the scope. Like similar to before, we build the we'll do the model configurations and build the model by saving everything, and there we'll open the file, new project. After building, we will have the STF file in this path. So that path we need to copy, paste in the root directory. You can give your name, your wished name for the project. Go to next. You need to ensure DS1103 is selected, and then import file. Choose the STF file, click finish. Now we are going to see the result. Go to plotter, we can take knob 2, and then go to view, switch control bar, variables, scope, that is the output of the system, input of the system, and then frequency. Now we can go start measurement. From this we can see input and output are same together. The RC filter just gives the input signal to the output. The cutoff frequency is very high, so there is no change in it, and we are getting the output same as the input. Everything is fine. So now we can go offline. Now we design a lead compensator. We need to check the result of the system across lead compensator. After connection we will continue. Sorry. So now we have connected the system across the lead compensator, and from the output we will stop it, and we will check the result. We can see the red, there is a slight phase difference with the green and red, and from this we can see the more. The red is slightly leading the green. The red is the output of the lead compensator, green is the input to the lead compensator. From this we can see the red is slightly leading the green one. So lead compensator is working fine. Now we are going for a closed loop system. We are considering the lead compensator as a system that is in hardware, that is will be presented here, and we are giving a closed loop. Like the similar, we will go open this and go to code generation, make a SRT1103, remove this check-in solver, remove this to installer, click apply and do OK. Then we will build the model after copying the file. After that we will open the STF file. These steps are common for all the experiments. Go to file, new project, copy the path where the system is there, next, import the file. Now we are going to see the error and the output. So go to plotter, this one, view, switch control bar, variable. The output of the sum is the error, and the input to the scope is the output of the system. That is, output of the sum block, this is the error, and input to the scope is the output of the system. Now we go to home, start measuring. From this we are seeing where the system is unable to track the reference. So now we are going to add a PID controller. You can go offline. Now we go for the system with PID. The system is the lead compensator, is considered as a system which is present here as the hardware, and PID we are using as without PID we didn't attain the steady state. So with the PID we are trying to attain steady state value of 1. So with the same thing we will go to the configuration, make this RTA1103, uncheck this one, uncheck input and initial state and click OK, and then we will build it after saving this in the file, and we are opening the file and running it. With the same as we did before, we will do the same steps. Go to new. I will do it again. Go to new, experiment, next. We will import the file, new build file, finish. We will take 2 plotters to see the error and the output, and then go to view, switch control bar, variables, small dot, sum. Output of the sum is the error, and input of the scope is the output of the system, that is closed loop system. Then we'll go to home, start measuring. From this we can see the output is measured settling at 1, and the error is 0.00, very small error. That is, here we are getting 1 and the error is very small, and we can stop this.